Unit 3 is all about thermodynamics, so let's see how do you work out the practice problems that are provided with part of that A+ College Ready curriculum. There are 32 questions here. The first one is basically a vocabulary question. Since entropy is a measure of disorder, which one of the answer choices best fits that idea of disorder? Some students might guess D because D is a component of entropy. Entropy and particles, though, need to become more and more disordered, so B is the best choice. For number 2, this is a stoichiometry question. So the balanced equation is given, and the delta H for the reaction is shown as negative 126 kilojoules per mole. So the first step is always to take the number of moles and then use the information from the balanced equation to solve for what you're looking for. So the setup looks like this. This is something that students should be able to do without a calculator. Notice in the setup that basically it becomes half of 126, and half of 126 is 63. Notice that there is both a positive 63 and a negative 63. Because the question says, are released, you just want an answer. It shouldn't have a negative sign. So how much heat in kilojoules are released, that would be positive 63 kilojoules. In number 3, you start off with a lot of reading that may or may not have to do with the question. And actually it has little to do with the question. But again, this is stoichiometry. The only difference here is that first you have to change from grams to moles and then use the balanced equation. So the setup looks like this. You're going from 16 grams and using the molar mass of 78.18 and then using the information from the balanced equation to generate an answer. You could use a calculator for this and you would find an answer. You can also do mental math and approximate the answer. In this setup, 16 divided by 78.18 is pretty darn close to 1 to 5. Because 16 goes into 80 5 times, we can kind of reduce that fraction. So if students had to approximate and not use a calculator, then they could go 1 over 5. And then from that, they ought to be able to look at the numbers there and come up with the correct answer. So 1 over 5, and then there's another 2 on the bottom, really becomes 6535 over 10, and 6535 over 10 becomes 653. There's only one answer that's even close to that, and so that would be answer D. Number 4 is another stoichiometry problem. The setup is going from grams to moles and then using the information. This is something that students should be able to do without a calculator because, again, they're giving you basically 1/10 of a mole of barium. Number 5 is a calorimetry problem. Q is equal to mc delta T. In this case, you're looking for Q, not of water, which is normal, but instead for lead. So you're plugging in the mass of the lead, the C value for the lead, and the change in temperature. And the change in temperature is just 20 degrees. Notice that this math could be done in your head, and there's no calculator required because basically you get 10 times 0.13 times 20, and that ends up being 1.3 times 20, and you can see that the answer becomes 26. Number 6 disguises itself as a calorimetry problem when in truth it's actually a calorimetry problem with a little bit of stoichiometry. So the first setup is to go from 13.9 grams of sodium hydroxide to moles, and then using the heat, which it states is 44.4 kilojoules per mole, and you get a final answer of around 15,000 joules. Now notice that the answer comes out to be 15.4 kilojoules, but we're going to need the number in joules to plug it into Q equals mc delta T. So if we plug the answer in joules in, we want the mass of not only the water in the cup, but we also want the mass of the sodium hydroxide because it is the entire contents of the cup that is warming up times 4.18. We can find a delta T, and the delta T ends up being 14 degrees. One final trick here, we need to know whether it got 14 degrees warmer or 14 degrees cooler. So if you look in the question, notice that the delta H is negative 44.4. That means it's exothermic. And since it's exothermic, that means it had to get 14 degrees warmer. And if it got 14 degrees warmer and started out at 23, then the final temperature has to be 37. Notice both answer choices are given for if you add or subtract 14 degrees. Number 7 is a Hess's law problem where the students have to decide whether to keep or flip each one of the given equations to produce the target equation down here. We keep the first equation because Fe2O3 is on the left-hand side in both the original equation and in the target, but we multiply everything through by 3 because in the target equation it is 3 Fe2O3. So we do each one of the reactants and the delta H. For the second equation, we multiply through by 2 because in the final equation we want there to be 2 Fe3O4s, and in the beginning equation there was only 1. So I multiply the entire equation by 2, including the delta H value, and then all you have to do is add together the two numbers, the negative 84 and the positive 25, and that gives you the delta H for the target equation. Number 8 is the idea of heats of formation, where the delta H of the entire equation is equal to the delta H of formation of all the products minus the delta H of formation of all the reactants. We know the delta H for the entire equation is negative 186. We know that hydrogen and chlorine are elements in their standard state, and so they have a value of 0. Plugging in for it, we can solve for the value of HCl basically being half of negative 186. Number 9 is the same equation. This time a little bit more complicated because you don't have a bunch of zeros you're plugging in. But again, the delta H of reaction is all the products. And notice we multiply each heat of formation times the coefficient from the balanced equation, and that's how we derive the final answer. Number 10, the directions tell you that the reaction is unbalanced. So the student will have the added step of balancing the equation. So this is the balanced equation, and it doesn't balance easily. The delta H again is just the heats of formation of all the products minus the heats of formation of all the reactants. Same kind of question. Students need lots of practice in order to avoid all of those negative signs with minuses and stuff. Lots of practice is needed. We plug in the numbers from there. This time you're given the delta H of the final reaction. The only one you don't know is the HCl, and you solve for the problem. So far we've done heats of formation, we've done a Hess's law, and there's been a bit of a calorimetry problem. So this is the last way to find delta H. This is bond energies. Bond energies is all the bonds that have to be broken minus all the bonds that are formed. So we set it up as all the bonds that are broken minus all the bonds that are formed over in products. We plug in the numbers given to us in the problem for all the bonds that are broken, and then subtract all the numbers for all the bonds that are formed. You could have taken a shortcut here by realizing that the CH bond represented here by the 413 is both broken in the beginning and then formed at the end. So the shortcut would be to just cross those out altogether, because in the end they just cancel each other out. Same type of problem. So we take all the bonds that are broken, we subtract all the bonds that are formed, and we get the final answer. Another example of a question that gives the student a lot of reading that really has nothing to do with the problem, but we want them to be ready for the AP exam, and that's the kind of questions that they'll see there. So this is finding delta S, and students use the data given to them in a table, and again it's the delta S of formation of all the products minus the delta S of formation of all the reactants. Number 15 is the very same type of problem. It is the delta S of formation of all the products minus the delta S of formation of all the reactants. Don't forget to multiply each number by the coefficient in the balanced equation. One more time, same type of problem, all the products minus all the reactants. This time we're looking for delta H, but it's the same type of problem, all the products minus each one of the reactants, giving us a final answer of 790.4. Very same setup, all the products minus all the reactants, and you get your final answer there. Same type of problem, except this time delta G instead of delta S or delta H. Same setup, and you can see this on the sheet with all the equations, but again, it's just products minus reactants, and you get a final answer. And number 20 is again, very same setup, plugging in the numbers, finding the final answer. Number 21 is one more time the practice of the delta S of formation of all the products minus the delta S of formation of all the reactants. And we get the final answer, negative 166.4 joules per mole Kelvin. Number 22 then incorporates everything they've learned up to this point with delta G, with delta H, with delta S, and then finding K. So we start with the equation delta G is equal to delta H minus T delta S. We plug in the numbers given to us to find delta H. We plug in the numbers given to us to find delta S. And then we can plug in those numbers as well as the temperature into the delta G equation. Notice in this step that we changed the negative 191 joules to 0.191 kilojoules. Since the delta H is in kilojoules, very important to make the delta S matches in units. Since delta G is negative and thus is thermodynamically favorable, we would expect a K value greater than 1. To find that, we use this equation where we're plugging in an R unit. The R unit in this case is 8.314 joules per mole Kelvin. So the negative 139 kilojoules needs to be changed to a negative 139,000 joules to make everything fit. We plug in the numbers, we get that the natural log of K is 56, and by taking the inverse natural log, we get this as a K value. And it's greater than 1, really hugely greater than 1. Notice that all the answers are greater than 1, so it makes it a harder problem to guess. Number 23 is basically the opposite tact from number 22. This time you're given a value for K. Notice that it's less than 1, and that typically tells you that it's not thermodynamically favorable. So we're expecting delta G here to be a positive number. So again, we use this equation. We plug in the value for R, the value for temperature in Kelvin, and natural log of 0.48, and you get 1,818 joules per mole. And since the question asks for kilojoules per mole, we just move the decimal place. Number 24, same type of problem. This time you have the ability to find delta G by plugging in for delta H, plugging in for delta S. Notice that delta S is in joules and delta H is in kilojoules. So when we substitute into the delta G equation, again, we have to make sure the units match. And when we do that, we get a value of negative 91.1. Of course, we're not done yet. We go to our other equation, and we plug in the numbers, remembering to put it in joules again, because the value for R is in joules per mole Kelvin. We find that the ln of K, the natural log of K, is 36.8, and we get a value of 9.59 times 10 to the 15th power. A little bit of a sanity check. K greater than 1 means it's thermodynamically favorable, and that makes sense because the delta G value is negative. Number 25 is a calorimetry problem. So we use the formula Q is equal to mc delta T. We take the numbers from the problem and plug them in. So we know the energy was 29.0 joules, the grams of lead was 15, and then we calculate the temperature change because we know it started at 22 and went up to 37. And when we do the math, we get 0.13. For number 26, students have to figure out what kind of question exactly is it. Well, I don't see heats of formation. It's not a calorimetry problem. It's not a bond energy problem. They're giving you two equations and asking you to match a target equation. So this becomes a Hess's law, keep or flip. So this is the first equation. If we're trying to match this to the target equation, notice we want N2 on the right-hand side. So all we do is flip the equation, and when we flip it, we also flip the sign of delta H. There's no need to multiply it by anything because there's one N2 in the original equation, and in the target equation, there's one N2. For the second equation that's given to you in the problem, notice in the target equation, NO2 is on the left-hand side, but in the equation given to us, NO2 is on the right-hand side. So we have to flip this equation, and when we flip the equation, we flip the sign of delta H. And now the two equations given to us add up to the target equation. So all we have to do is add up the two numbers, the negative 180.7 and the positive 113.1. 27, again, is just a heats of formation problem. So it's all the products minus all the reactants. Notice in this case, they don't tell you what the heat of formation of oxygen is. The student should know that an element in its standard state has a delta H of formation of 0. Also notice that not all of the numbers are used from the table. 28 is a simple, do they understand the idea of exo and endothermic? So if it absorbs heat, then we know that it's endothermic, and this is something that students struggle with. Endothermic has a positive delta H, so they're just matching up their knowledge of endothermic absorbing energy with a positive delta H. Number 25, notice they don't say K, but they do say the equilibrium constant is 5 times 10 to the 8th. This is a number much greater than 1, and a K value greater than 1 indicates that it's thermodynamically favorable. So we use this equation, making sure that we plug in all the numbers given to us. And when you solve, you get negative 49,626 joules. But notice all the answer choices are in kilojoules per mole. And so you round up and change it to kilojoules. Number 30 just asks them to interpret a diagram. So first of all, is this a positive delta H or a negative delta H? You start here at 40 and you end up down here at 20. Notice that this is potential energy, or PE. Thus, as you go from potential energy to kinetic energy, there's energy actually lost. That is why there's a drop in potential energy. It's being converted into kinetic energy. So the change in energy here is 20, and it should be a negative 20 because the energy is being lost. So number 31 is a calorimetry problem. Obviously, there's no equation to keep or flip, and there's no heats of formation. So first we start with calorimetry. We want the mass of not only the solid that's dissolving, we also want the mass of the water. And notice that for the sake of mental math, 21.2 and 78.8 adds up to 100. We put in 4.2, that's given to us in the problem, and then we put in the temperature change. It got all the way up to 67, and the low was 23. And so when we do that math, we get 18,480 joules. Now the question doesn't ask you how much energy, it asks you for the molar heat of dissolution. So now we have to figure out what it is in kilojoules per mole. So we take our number of joules and we convert it to kilojoules, and we divide it by the 0.5 moles of LiCl. Basically, we take 18.48 and we multiply it by 2. And we get an answer around 37 kilojoules per mole. Now, it needs a negative sign because it did get warmer, and the negative sign shows that it's an exothermic reaction. So the final answer would be negative 37 kilojoules per mole. Take the time to realize that the answer was also given as 9.25, which would happen if you took 18.48 and instead of dividing it by 0.5, you multiplied it by 0.5. So the answer choice is there even if the student got the math wrong. For number 32, this just becomes a stoichiometry problem, and then once you have the stoichiometry problem, it asks you to then find the final temperature. So just like 31 was a combination of Q is equal to MC delta T and then plugging in moles, this time we're going to actually start with grams and find moles. We're going to use the numbers from the equation, 123 kilojoules for every 2 moles of aluminum hydroxide, and get an answer. Then we're going to use Q is equal to MC delta T, but remember to change the 61.5 kilojoules to joules. We plug in the mass not just of the sulfuric acid, but also the mass of the aluminum hydroxide. Because after all, in this container, what is actually getting colder? And the answer is both the aluminum hydroxide and the sulfuric acid mixed together. So we need both masses. Again, we use 4.2 and we get the change in temperature. And the change in temperature ends up being 16.7 degrees, which rounds to 17 degrees. And then what's the final temperature? Well, delta H has a positive sign, which means it's endothermic, which means the temperature should go down. It should decrease. So if you started out at a temperature of 38 degrees and you went down by 17 degrees, you'll get the final answer of 21 degrees.